Hello everyone, my name is Rakshit Singh and today I will be discussing an essential area of operating system security, OS level memory encryption with a focus on ARM based processors. As we dive deeper into the realm of cybersecurity, we must address the increasing need to protect the integrity of data, particularly in memory. ARM processors have become the backbone of mobile, embedded, and IoT systems, used in everything from smartphones to medical devices and even smart home appliances. This widespread use makes securing memory in these systems critically important. In this session, we will explore how ARM systems leverage OS level memory encryption techniques to secure sensitive data, including encryption mechanisms such as TrustZone, memory tagging extensions, pointer authentication codes, and others. Let's take a closer look at these topics and understand how they work together to safeguard memory. Motivation. To understand why OS level memory encryption is necessary, we need to first grasp the vulnerabilities inherent in system memory. Data stored in a system's memory is extremely valuable but also highly exposed. If an attacker gains physical access to the memories, they could extract sensitive information, be it personal data, passwords, encryption keys, or credentials, leading to severe security breaches. One of the most common attack vectors is physical memory compromise. Attackers can exploit vulnerabilities in a device, hardware, or OS to extract unencrypted data directly from memory. Now imagine this risk is not only confined to desktops or servers, but extends to billions of devices globally, including smartphones, IoT devices, and other ARM based embedded systems. OS level memory encryption is a direct response to mitigate these risks, ensuring that even if an attacker gains access to memory, the data remains unreadable and unusable. As we dive deep into OS level memory encryption, it's useful to link this to the concepts we have covered in the class. For instance, in access control, we have learned about how systems prevent unauthorized access. OS level memory encryption serves as an additional safeguard, ensuring that even if an attacker bypasses access control mechanisms, the data remains secure. Similarly, in our study of rootkits, we saw how attackers can exploit system vulnerabilities to gain persistent access. Effective memory encryption can help mitigate such threats, making it harder for rootkits to access or tamper with sensitive data. Introduction. In today's presentation, we'll first define OS level memory encryption and examine how it works, particularly in ARM based processors. Then we'll look at the critical security features embedded in ARM processors that are designed to protect memory. These include technologies like ARM's TrustZone, memory tagging extensions MTE, and pointer authentication codes PAC. Lastly, we'll walk through a real-world example of how memory encryption is implemented and touch on the challenges and future research opportunities in this field. Let's begin by understanding the basic concept of OS level memory encryption. Background, OS and ARM memory handling. To appreciate how ARM processors implement memory encryption, it's essential to first understand how memory is managed in a typical operating system. Systems divide memory into two key regions, user space and kernel space. The user space is where applications and programs run, while kernel space is reserved for operating system and critical system processes. ARM processors use a memory management unit, MMU, which enforces access controls between these two regions. This separation ensures that the user applications cannot directly access kernel memory. The MMU plays a vital role in managing this isolation and preventing unauthorized access, which is the foundation for implementing encryption techniques. By securing memory access between user and kernel space, the system provides a critical layer of defense against various types of attacks. But what happens when we need to secure the data in memory itself? Let's explore the role of OS level encryption. Overview of OS level memory encryption. OS level memory encryption is a method where the operating system itself is responsible for encrypting and decrypting the data in memory. It ensures that sensitive data is always encrypted, even when it is actively used by running programs. Unlike traditional file encryption, where encrypts data at rest on storage, OS level memory encryption protects data while it is actively being used. This is crucial because, as we mentioned, even if an attacker can compromise the physical memory, encrypted data will remain unreadable. This method differs from hardware based encryption, as OS level encryption is more flexible and it can be tailored to different use cases. It also ensures that all data in memory, not just files or application, is encrypted, offering comprehensive security for sensitive information. ARM TrustZone. One of the most powerful security feature ARM processors offer is TrustZone. TrustZone essentially creates two separate environments in the processor, the secure world and the normal world. The normal world is where typical applications and services run, whereas the secure world is reserved for security operations, such as cryptographic functions, key management, and secure boot processes. This separation is enforced at the hardware level, ensuring that the two worlds are strictly isolated. For example, when sensitive data like encryption keys are processed in the secure world, even if the normal world is compromised, the secure data remains inaccessible. TrustZone plays a pivotal role in safeguarding systems from attackers who might attempt to exploit vulnerabilities in the normal world. In mobile devices, for instance, TrustZone is used to secure biometric data and ensure that even if the device is compromised, critical information like fingerprint or face recognition data remains safe. Memory tagging extension, MTE. Another important security feature in ARM processors is memory tagging extension, which is designed to protect memory corruption attacks such as buffer overflows and use after free vulnerabilities. MTE tags memory regions with metadata. When a program tries to access memory, the hardware checks whether the memory access matches the tag. If there's any inconsistency, like an out of bounds memory access or a mismatch between the tag and the memory, the system raises an exception, stopping the attacks in its tracks. This mechanism significantly reduces the risk of attackers exploiting memory corruption vulnerabilities, which are common in many types of cyber attacks. By proactively preventing such attacks, MTE adds another layer of security for ARM-based systems. Pointer Authentication Codes, PAC. ARM processors also employ Pointer Authentication Codes, PAC, which protect against a specific category of attacks known as return-oriented programming. ROP attacks allow attackers to hijack function pointers to control the flow of execution in program. However, with PAC, ARM processors attach cryptographic signatures to function pointers. Every time a pointer is used, the system verifies the signature. If signature is invalid or tampered with, the system prevents the operation from proceeding. This method ensures that only trusted pointers are used, making it far harder for attackers to control execution flow. PAC is a crucial defense mechanism against sophisticated attack techniques that manipulate pointers to execute malicious code. Other encryption methods in ARM-based systems. In addition to TrustZone, MTE, and PAC, ARM processors also implement other memory protection techniques. One such method is memory scrambling, which randomizes the arrangement of data in memory. This makes it difficult for attackers to locate specific data even if they gain access to the memory. Furthermore, ARM processors often include hardware-accelerated encryption engines such as AES, Advanced Encryption Standard, which provide fast and efficient encryption without compromising performance. These hardware engines allow for memory encryption at a low overhead, making them ideal for resource-constrained devices like smartphones or IoT systems. By combining multiple encryption methods, ARM processors deliver a layered security approach. ensuring that memory is protected in various ways, even if one defense mechanism is bypassed. Apple case study. To see how these encryption methods are implemented in real-world application, let's look at Apple's A series processors, which are based on ARM architecture and used in iPhones and iPads and Macs. Apple's A series processors incorporate a range of advanced security features. For instance, they use Secure Enclave, a dedicated mechanism for handling sensitive tasks like encryption and biometric authentication. The Secure Enclave operates within its own secure memory area, isolated from the rest of the system, and performs real-time encryption and decryption of sensitive data. Similar is the case of M series processors like M1, M2, M3, M4 that are used in Macs and iPads. Apple also employs full disk encryption, secure boot processes, and memory encryption to protect user data. All of these features work together to ensure that even if physical memory is compromised, the stored data in it remains encrypted and unreadable. Security challenges and limitation. While OS level memory encryption is an effective security mechanism, it's not without its challenges and limitations. One primary concern is performance overhead. Encryption and decryption requires additional CPU cycles and memory bandwidth. This can impact the overall performance of the system, especially in devices with limited resources like IoT systems or low-end smartphones. Balancing security and performance is a key challenge in implementing memory encryption. Another challenge is the lack of standardization across different operating systems. Different OSs such as Android, Linux, and iOS implementing their own encryption methods and APIs, leading to inconsistencies in encryption implementation. This can create security vulnerabilities, especially in cross-platform applications. Additionally, the isolation between secure and normal worlds in ARM processors can be weak in some cases. If the isolation is not enforced properly, attackers can exploit it to escalate privileges and access secure data. Finally, side channel attacks, which exploit weaknesses like cache patterns or electromagnetic emissions, can potentially bypass encryption and leak sensitive data. These type of attacks are difficult to defend against and remain a significant security concern. Future work and opportunities. Looking forward, there are several key areas where OS level memory encryption can be improved. First, the standardization of memory encryption across platforms is crucial. A unified standard for encryption could streamline implementation and ensure that encryption is more robust across different devices and OS environments. Next, machine learning offers exciting opportunities for dynamic threat detection. By analyzing memory access patterns in real time, machine learning models can predict potential threats before they materialize, allowing for a more proactive defense against novel attacks. Lastly, for resource-constrained devices, optimizing encryption techniques is essential. Lightweight encryption methods that don't significantly impact system performance are crucial for IoT devices, embedded systems, and smartphones. Conclusion. In conclusion, OS-level memory encryption is a fundamental component of modern cybersecurity, especially in ARM-based systems. Technologies like TrustZone, MTE, and PAC provide robust security for data and memory. By utilizing both hardware and OS-level encryption, ARM processors protect sensitive information even in the event of physical memory compromise. However, challenges like performance overhead, lack of standardization, and the threat of side-channel attacks still exist. As we move forward, focusing on standardization, machine learning for threat detection, and lightweight encryption for resource-constrained devices will be critical for further enhancing OS-level memory encryption. References. Finally, here are the references I used for this presentation. These include academic papers, official ARM documentation, and resources from industry leaders that provide in-depth insights into the topics discussed today. If you are interested in diving deeper into any of these topics, these resources are a great starting point. Thank you.